Well, good afternoon, friends, or good evening, as the case may be, wherever you may be located in the world. Welcome back. I'm John Kemp, and tonight our webinar series continues with a discussion on the nutrition, what is required to produce exceptional quality stone fruit. So the presentation tonight is going to be quite brief, to the point, and I want to speak specifically to what are the nutritional requirements to produce exceptional quality stone fruit. What does it take to produce really large fruit that are really firm? And of course, this information also applies to other types of, well, essentially any fruiting crop. I want to talk specifically about the nutritional requirements at different parts, different points of the fruit development period, such as cell division, cell expansion, and what exactly we can do to produce much higher quality fruit. So I'm going to talk about a couple of examples, a couple of farms that we've worked with that have produced some really exceptional results of fruit quality, size, and so forth, and how we did it. So it's going to be quite straightforward. If you have any questions throughout the presentation, I'm alone here on the webinar tonight. Type in any questions that you have down below. You can see at the bottom of your screen, there's a Q&A box. You can ask any questions there. And as soon as I'm through the slide deck, then I'll open it up to you for a discussion and answer any questions that you might have. So it's going to be fun. Looking forward to it. All right, so I'm going to begin by sharing my screen. And we're going to start here. So the context, the place where we first learned a lot about how to manage fruit quality was actually in cherry production, and then a lot of that information transferred over to apple production. And now we've adopted some of the things, some of these aspects of managing fruit quality to all of the farmers and all the growers that we work with. What we learned is that we can actually shape fruit size, fruit firmness, and aroma and flavor to a substantial degree just before and during the blossoming and pollination period and the cell division period, and then later on through the fruit filling period as well. So we believe that we can actually determine fruit size and what that future potential fruit size might be based on how we manage attrition during the cell division period and during the fruit fill period. And I want to describe exactly how we're doing that and how we're producing those results. We also believe that we can substantially reduce the percentage of fruit gradeouts. And we've actually seen some quite remarkable numbers that I want to talk about in a little bit on peaches and nectarines and apples, for example, where historically, gradeouts, number two fruit, or fruit that don't qualify for the premium packouts, might represent as much as 35 to 40% of the total harvest. And in a single year, we've been able to drop that number down from 35 to 40% down to as little as 5% or even less, which is a really, really big deal from a profitability perspective. So an example of some of the work that we've done on, this is one farm on Simonian orchards in California. This was in 2017. So we started working with Jimmy Simonian in November of 2017. They did some fall soil applications of Rejuvenate and Spectrum. And we started in the spring at the blossoming and pollination period with a series of foliar applications to balance the nutrition right at and during the cell division period, and then later on during fruit fill, with some fairly remarkable results. So with Simonian orchards, we were working with nectarines and peaches, plums, and then also with some grapes and some other crops later on in the season. But nectarines, peaches, and plums were the major early crops that we were working on that we were able to produce some very nice responses. So in 2017, with the addition of the AEA program, we were able to see some really substantial yield increases. So for these are numbers on the nectarines and the peaches, and these fruit were thinned by hand to in round numbers of approximately 900 fruit per tree. And so if we wanted to, so the 900 fruit per tree number is the exact same number that has been historically. So we had 900 fruit per, Simonian was targeting 900 fruit per tree in 2015 and 16 and 17 and so forth. So the increased yield numbers did not come from increased number of fruit per tree. Instead, it came about as a result of increased fruit size. So when you look at this, 4 out of the 6 varieties had quite substantial yield increases, ranging from a low of 16% to a high of 29%. And then 2 of the nectarines had slightly lower yields, from a 19% decrease in one field to a 12% decrease in another. And these were actually, we believe, the effects of overthinning and taking too much fruit off of the tree. So in addition to the yield increase as a result of increased fruit size, when we looked at the data of what the actual largest, or what the number one, so this is the data for the number one fruit of grade 1, which is of course premium priced, and we saw the largest yield increases in that fruit segment specifically. So as much as a high of 53% yield increase in number one fruit, all the way down to a low of a 14% yield increase in number one fruit. So when you combine that effect, where we had much larger fruit and thus increased yields, and we had a higher proportion of number one fruit, that of course, both of those factors compound to contribute to quite a substantial increased profitability per tree. What this slide was communicating is that when you combine the yield increase and compound that times the higher grade, that produced on 4 out of the 6 fields produced a very substantial revenue increase, all the way up to a 40% revenue increase. So really substantial revenue increases. So then we also observed a shift in, so that shift then is also reflected in this is another perspective, another graph of looking at the fruit sizing on the nectarines. So nectarines are case counts of 72s or 56s, 48s and 56s. And the case count of 72s this last year, market prices were about $12 per case. And cases of 56s were about $24 per case in general round numbers. So when you look at these, and remember that each of these trees has roughly 900 fruit per tree. So if you have 900 fruit per tree that is primarily in the 56 size range, that is worth $24 a case, as compared to a tree that has 900 fruit per tree that is mostly 72s, that is worth $12 a case. There is, I did this math earlier, and just off the top of my head, when a tree has primarily 56s, the per tree value is about $380 US. And if you have a tree that is primarily 72s, the yield is worth about $180 US. So obviously there's some, they're not perfect. You will never have a tree that is 100% one or the other. There's a blending effect, but that's a really substantial difference in overall yield and overall value and revenue. So this graph is a shift, it reflects the shift of how yields shifted from 2016 having a much higher proportion of 64s and 72s to 2017 having a much higher proportion of 48s, 50s, 56, and 64s. So we were able to shift the yield size, or the fruit size, up into the premium price range quite effectively. So how do you do that? How do you actually make that happen? Well, to provide a bit of an explanation for some of the important minerals, understanding what is happening, it's important to understand a couple of key nutrient interactions. So specifically, I want to focus on this nutrient interactions diagram that we've developed, and talk about calcium and potassium. So I've spoken about this diagram before. Some of you may have seen or heard of it before, but we've developed this diagram to reflect how we see nutrients interacting and behaving with each other inside the plant. So this is not a soil nutrient interactions diagram. This is specifically for what happens inside the plant. And it isn't perfect. There are some discrepancies on it, but it is much simpler and easier to understand than the Mulder chart. So if you look at this chart, it's divided into quarters. On the left half, we have all the cations. On the right half, we have all of the anions. On the upper half, we have all of the major nutrients, the macronutrients. And in the lower half, we have all the trace minerals. So the key piece to think about when we think about mineral balancing in soils, in soils we have this concept of cation exchange capacity, CEC. We understand that each cation in the soil profile can only adsorb so many. We understand that each clay particle can only hold so many minerals, can only hold so many nutrients. And although it is conceptually different, it is also conceivable. We should also think about each cell inside the plant, each cell in our own bodies also has a finite mineral holding capacity. They can only hold so many cations and they can only hold so many anions. So if you look at this chart let's look at the upper left-hand quadrant where we have calcium, potassium, magnesium, sodium, and ammonium. The key thing to think about these 5 cations is that inside the plant, we observe them constantly antagonizing each other. Each cell can only hold so many of these cations. So if you have a surplus of one cation, let's say calcium, for example, you can actually produce a potassium deficiency. Or vice versa. If you have an excess of potassium, it can actually induce a calcium deficiency. Even though there may be a generous supply of calcium in the soil profile, or even in the tree tissue, the calcium may not be able to move to where the plant actually needs it. So this is a very foundational piece, understanding specifically around these 2 nutrients. Inside the plant, calcium and potassium are intensely antagonistic. And so when we look at all of these physiological fruit disorders that are calcium-related disorders, such as bitter pit in apples and bitter rot, blossom end rot in a broad variety of different fruit, these are often referred to as calcium deficiency problems. But in reality, they may not be a calcium deficiency so much as they are a result of a calcium deficiency in the fruit. But that calcium deficiency in the fruit may be the result of excessive potassium inside the plant tissue or in the soil profile that is preventing calcium from moving into the fruit. So this is why for many fruit growers, you can apply tremendous amounts of calcium as a foliar and still get only a very limited crop response and a fruit quality response, because the problem isn't really a calcium deficiency problem. It's a potassium excess that is creating the calcium deficiency. So this is a very important piece and is very important for us in talking about these next 2 pieces in how we manage for fruit quality and producing exceptional fruit quality. So let's speak for just a moment about the 2 key stages of fruit development. So after a blossom pollinates, you have, for a 10 to a 14-day period, depending on the species and the environment and climatic conditions, you have what is referred to as the cell division period, where you have this very rapid expansion of the total number of cells inside the embryo. So starting with 2, 4, 8, 16, 32, 64, 128, this very rapid linear progression where you have this explosion in the total number of cells. So that total number of cells is going to determine the potential future fruit size. It's not going to determine what the future fruit size will be, but it's going to determine the potential for that fruit size. Because the more cells that you can produce in that 14-day window, the larger the future fruit can be. And here's the really key piece, is that in this 10 to 14-day window, we want to accomplish two things. One is we want to extend this window as long as we can. That is, of course, based on environment, temperatures, and so forth. But secondly, within this window that we have, this golden opportunity, we want the fruit to produce, this embryo to produce the largest number of cells possible. The more cells we can produce, the larger the future fruit can potentially be. So the number of cells that is produced in this window is limited by calcium availability. The more calcium we can move into the embryo in this 10 to 14-day window, the more cells can be produced and can be established in that window. Because the reason calcium is the limiting factor is because calcium is needed to form the cell membranes for all of these new cells. So amongst, obviously there are other environmental and climatic conditions as well, but from a management perspective, we need to think of calcium as being the key limiting factor. So in this golden window, these 10 to 14 days, we want to move as much calcium as possible into the embryo. This is the period when we need to have potassium levels be very low. At this point, we want potassium levels low inside the plant so that we don't have excess of potassium preventing calcium absorption and transfer into the embryo. So then when we look at the second stage, so after the cell division stage, after this 10 to 14 day period, the fruit now switches to cell expansion. So for the remainder of the fruit fill period, all the way up until the fruit is actually harvested, each of these millions of cells that has been established is now going to be filled with sugars, with water, with proteins and nutrients. And so we get this very rapid cell expansion. So this cell expansion, so cell division and the total number of cells determines the potential fruit size, but cell expansion determines the actual fruit size. We are limited in this cell expansion period by how much sugars that the tree or the plant can produce and actually move into the fruit. So there's two parts, there's two components of this. The first is, of course, the actual sugar production. We want trees that are producing large volumes of sugars, particularly in the spur leaves, because a large proportion of the sugars in the fruit actually come from the spur leaves. And secondly, once we produce a large volume of sugar, we need to transfer that sugar into the fruit. So during the fruit fill period, for the sake of discussion for just a moment, let's assume that we have adequate levels of photosynthesis and we have enough sugar production. That's another conversation in and of itself, is how do we increase photosynthesis, and we'll get there in a moment. So let's say that we have adequate levels of sugar production. Now we need to move that sugar into the fruit. And so fruit fill and sugar transport into the fruit is limited by the potassium supply. Inside the plant, potassium is essentially the sugar transport locomotive. It connects to sugars in the leaves during and after photosynthesis and transports those sugars to the sugar sinks. So you have three major sugar sinks. You have the root system, you have the new growth tips at the top of the plant, the apical meristem, and you have the fruit. Now, when potassium transports sugars to the new growth tissue at the top of the plant or to the root system, it releases those carbohydrates and it goes back up to do the same job over again. So potassium is constantly cycling through the xylem and the phloem tissue, moving sugars around wherever they are needed. But when potassium moves sugars into the fruit, there is essentially a one-way entry gate into the fruit for sugars and consequently also for potassium. So any fruit which contains a large amount of sugar, whether it's a tomato or a peach or a nectarine or a watermelon, whatever the case might be, There will also be a very high potassium requirement during the fruit fill period. So we find that this period, later on during cell expansion, is when we benefit from the potassium applications. If we put on a potassium application early during the cell division period, it actually causes us problems because of limited calcium mobility into the embryo. So we need to apply the potassium a little bit later. So as an example of this is an example of SAP analysis report on this was one block of Simonians nectarines. And if you look at this data, for those of you not familiar with a SAP analysis report, we have two numbers for each of these parameters, for each of these minerals. So if you look at potassium, we have the upper number is 6,400 parts per million. And just below that, we have 8,400 parts per million. That means, so the top number, 6,448 parts per million, is the potassium level at the new growth, the last fully matured leaf. So the new growth at the top of the plant. And the bottom number, 8,400 part per million, is the potassium level in the old leaves, either at the bottom of the vegetative growth, or in this case, this sample was collected shortly after blossoming and bloom during the cell division period. This old growth number, or the old growth sample, was actually collected from a spur leaf. So we can see that the spur leaves have 8,400 parts per million potassium. The new leaves and the new growth shoots have 6,400 parts per million potassium. Calcium, we have 36 and 27. So we have a very wide ratio between the potassium and calcium ratio. We have 180 to 1 ratio on the new leaves and the vegetative growth, and a 310 to 1 ratio on the spur leaves. So this is a problem that we have such a wide ratio. We would want this ratio to be much narrower and have higher levels of calcium and lower levels of potassium at this critical stage, because we know that this is going to influence the number of cells that will be produced during the cell division period. So if you look at a comparative SAP analysis, this is from another block of nectarines that had much higher fruit size, much better fruit size. Here we have a much narrower potassium to calcium ratio. So here we have 4,592 and 6,595 on potassium, and calcium 95 and 39 parts per million. So the potassium to calcium ratio on the vegetative growth now has dropped to 48, and the spur leaves is 171. So we have comparatively, we have almost half the ratio, or twice the calcium concentration relative to potassium. This will have a huge impact on fruit quality and firmness, and reducing calcium-related physiological disorders in the fruit. So where we actually first learned about the critical importance of these ratios at specific stages was when we were working with cherry production in Washington with Omeg orchards. And the objective, the goal that we were working for was, with Mike Omeg, was to produce very large, firm cherries that qualified for the export market. So we want both really large size and we need firmness as well. So in order to get good firmness, that means we have to have a large amount of calcium moving in during the cell division period. So we conducted an experiment. This was side by side, one block AEA treatment versus Omeg's standard grower treatment that he had been using for the prior number of years. And that standard treatment included a foliar application of 20/20, water-soluble 20/20 at 5 pounds per acre. Two applicants, one application pre-bloom and one application at post-bloom, right during the cell division period. So one of the key changes that we made was to pull out the 20/20. We said, no, we cannot, let's not put on the 20/20 early on during this cell division period, during the bloom period. We have to wait for the triple 20 application until we get to the cell expansion period. So as you can see, there was quite a substantial increase in the row size and the fruit size, where we generally increase the fruit size by one entire row number. And that, the numbers are missing from this slide for some reason, but that resulted in a net profit increase of $1,600 per acre, quite a substantial increase. So when you look at the treated versus untreated side, on the treated side, where this is the area where we kept out the triple 20, so there was no potassium application, foliar applications early on. Here we see we have potassium levels 46 and 4700, calcium 680, 680 and 650, and that is a potassium to calcium ratio of 6.7 and 7.1. So obviously this is a different tree, a different plant, and we're looking at very different ratios from what we were looking at in the nectarines, but these are really good numbers and really good potassium to calcium ratios when we're using this, when we're using the SAP analysis. So this was the treated side where we had removed the triple 20 application. Where the triple 20 application still remained, we had very different numbers. So if you look at the calcium levels on the prior test were 680 and 640, and here they're 534 and 763. So on the new growth, they're slightly lower. The old growth, they're slightly higher. But there aren't really any substantial differences on the calcium levels, but there are really substantial differences on the potassium levels. So if you remember, the potassium levels were 4,600 and 4,800, and here they are over 7,000. So we've gone from a ratio of 7 to a ratio of 9 and 13. So we have a much broader potassium to calcium ratio, and that ratio difference in the calcium and potassium during the cell division stage is what resulted in one row size lower cherry size. So a couple of additional points worth mentioning is one additional challenge to manage is, and that we sometimes see a problem with, is where you actually have excessive potassium and particularly excessive nitrogen during the fruit fill period tends to produce much larger, softer cells that don't produce firm fruit. So if our objective is firm fruit, working with Omeg on his cherry operation for the last 4 years, the last couple of years we have been producing cherries that on a FermTech machine are consistently topping out well over 400. And the last couple of years, we've had a number of fields that on the FermTech were 600 and 700 readings and greater in firmness. So it's actually possible you can produce really, really firm fruit by managing the potassium and the nitrogen applications later on, once you have provided adequate levels of calcium early. So before I move on, I'd like to speak for just a moment about photosynthesis, because to some degree, I'm including this as an assumption, as something that has to happen in order to produce these exceptional quality fruit. But it's actually something that we find is often not happening in trees the way that it should be happening, or the way that it has the potential to happen. So most fruit trees are, of course, this is dependent on the environment that they're in as well, but they're producing somewhere in the neighborhood of about 25 to 30% of their inherent photosynthetic potential. So when we look at photosynthesis, the question becomes, how do we, if a tree and the spur leaves in particular are only photosynthesizing at 30% of their efficiency, how can we move that number much higher and produce a larger volume of sugars to move into the fruit? So there's a couple of pieces to consider here. First of all, one of the pieces to pay attention to, particularly for all the spur-bearing fruit, which the stone fruit are, is that we want to produce the largest spur leaves possible. And to accomplish this, we need producing large spur leaves is dependent on how we manage nitrogen and zinc, in particular, those two, in the fall before dormancy. So we have found on the last 4 weeks before dormancy, putting on applications of urea and foliar applications of urea and zinc to produce really large vegetative buds transfers to a really large spur leaf size in the spring, which then, of course, gives us the potential to produce a lot more sugars. So that's one place to begin. And then in addition to that, once we have larger spur leaves in the spring, there are 4 key nutrients that need to be managed well to increase photosynthesis to a much higher level of performance. So the first one is magnesium, because it's the center ion of the chlorophyll molecule. The second is manganese, because it is needed for water hydrolysis. And we consistently find that when we add manganese, we get a substantial jump in photosynthetic activity and increased sugar production. The third is iron, because iron is also, it is not a part of chlorophyll, but is used to build chlorophyll. And then, of course, the fourth element is nitrogen. So we typically don't see problems with low levels of nitrogen limiting photosynthesis, but it's usually often the first 3, magnesium and iron and manganese, that are limiting photosynthesis flow. So when you address those 3 nutrients and make sure that you don't have a nitrogen deficiency as well, you can increase photosynthetic volume and sugar production by as much as 2 to 3 times in every 24-hour photo period. And of course, now when you have much larger volumes of sugar production, you can move that into the fruit, and that's going to translate to much larger fruit size. Another critical piece when we start thinking about calcium and potassium applications and how to time them to have the biggest impact, we should think of, from a management perspective, that foliar applications of calcium during the fruit-filled period are ineffective. This isn't entirely true. We do know that when we put on foliar applications of chelated chelated calcium, it needs to be in the chelated form, then plants are able to absorb that chelated calcium and transport it from the leaf to the fruit. Some chelates are much more effective at this than others. But as a general rule, in terms of fruit quality, our golden window is that 10 to 14 day window of the cell division period. Any calcium that we can get into the fruit at that point is going to have a much bigger impact on fruit firmness and quality than calcium that is applied later on. Because really what we want to do is we want to get calcium in early and then focus on potassium later. And if we can manage that dynamic well, then and focus on our calcium applications early, we're going to have much better fruit quality. So with the growers that we work with, we do still continue with calcium applications during the fruit fill period, but we front load it very intensely. We put the majority of the calcium applications on during cell division and even before cell division. So pre-bloom, post-bloom, and most importantly of all, in the fall applications, the last 6 to 8 weeks before dormancy, we want to move a lot of calcium into the tree through foliar applications, where it will go directly to the buds and to the budwood. So that means the following spring, we have high calcium concentrations already in the buds that now are going to move directly into the embryo. So that is what we have found to be one of the most effective and most powerful strategies. So how do you do this? How do you do this on your operation? I've described a number of tips and ideas already, fairly simple strategies. But the key is that before and during the cell division stage, we focus on foliar applications of calcium and manganese and boron. Why those 3? I've already described the calcium piece. We need calcium to move into the embryo at this stage. And boron, of course, is known to increase calcium mobility and allow calcium to move around in the plant more readily. So it actually will increase calcium flow into the embryo as well. The reason for a manganese application is because manganese serves as a potassium regulator. It's, for lack of a better analogy, it functions as the thermostat that both upregulates and downregulates potassium. Both it regulates potassium absorption by the tree, and it also regulates potassium mobility and translocation, particularly calcium translocation into the embryos and into buds. So what this means is if you have a soil that historically has high potassium levels, or if you have a tree variety such as Honeycrisp apples, which is genetically prone to hyperaccumulating high levels of potassium, or like the nectarine sap analysis that we looked at earlier, which has very high potassium levels and a very broad calcium to potassium ratio, when we put on manganese and we make sure that the tree has a generous supply of manganese, manganese will prevent potassium from moving into the embryo in high concentrations and displacing calcium. So you can actually allow calcium to move into the embryo much more readily with generous applications of manganese. This is something that we have found to be very effective at managing bitter pit and Honeycrisp apples, for example, where as the manganese levels increase, we see potassium levels dropping and calcium levels increasing and flowing into the fruit much better. So the manganese component is a very important component here that has not been considered historically. So, and then of course, when we talk about this being before the cell division stage, that can also be in the fall before the spring season. So actual post-harvest applications and making sure that we get this into the tree post-harvest can be a very important piece for producing an exceptional quality crop the following spring. So then at the pre-bloom and post-bloom applications, our recommendations, the growers that we're working with, we're putting on foliar applications of Holocal, which is a calcium boron product, and Accelerate. Accelerate is a product that we developed to increase pollination and to increase embryo development. It contains high levels of manganese, along with cytokinins and seaweeds and a whole bunch of other goodies, and boron. So the product mix, the product recommendations that we make are specifically for these three materials: Holocal, Accelerate, and boron. So Holocal and boron are relatively obvious. Accelerate is a material which contains manganese, seaweed, cytokinins, and a number of other trace minerals as well in small quantities, that is specifically designed to increase pollen strength and all the various reproductive tissues in a blossom, to make sure that we have very good pistil and stamen strength, pollen strength, pollen tube integrity, and so forth, so that we get really good pollination. And we find that an Accelerate will also, if applied early enough, not necessarily on tree fruit, of course, but on other crops, it will increase the number of blossoms and the number of buds on a given plant. We find that it's very effective for that purpose. So then, an additional piece that we include in our recommendations is post-harvest applications of magnesium, zinc, and urea. So the purpose and the intent, and of course you can combine this with applications of manganese and calcium that I talked about earlier. These are not exclusive. You can combine these applications. The purpose of the urea and zinc application in the fall post-harvest, just before dormancy, is to increase spur leaf size the following spring. I don't know what the data is on nectarines and peaches. But on cherries, for example, there's some research which is soon to be published, I believe, from Michigan State University under the supervision of Greg Lang, that indicates that the sugars on spur-bearing trees, the total sugar supply in a cherry fruit, as much as 60% or greater, can actually be coming from the spur leaves. So that's a huge number. That means even though we may have a lot of vegetative growth and large leaf biomass on the new vegetative growth, only a small amount of those sugars being produced are actually going into the fruit. So we need to have really large spur leaves. I don't know exactly how this translates to nectarines and peaches and nuts and other spur-bearing crops, but I would assume that it would be a similar proportion where we have a large proportion of the carbohydrates in the fruit are actually coming from the spur leaves. So it'll be very important to manage that well. So I know that many of you that are here tonight are actually from California, from the West Coast. So I wanted to also, if you aren't already connected with Jeff McInnes is one of our leading consultants in California and is working with a number of stone fruit growers in several different regions throughout the Central Valley. So here is Jeff's direct contact information. We will also include this information on our follow-up email that you will get following this webinar. And you can feel free to reach out to Jeff directly because he has a lot of, Jeff is the one that put the recommendations together and has been working very closely with Simonian, the data that I shared earlier. And he has a really good understanding of how to put these pieces in place on various operations. So with that overview, I've put out a lot of information fairly quickly, and I'm going to open it up for any questions that you might have. So if you have any questions or comments, please share them below in the question box, and I'm going to go through those. So let's start here with John Warmerdam asks a question. Can an application of calcium in the early part of the season have enough time to have an effect, or only restricting potassium also as a passive effect? So if I understand your question correctly, I would say in our experience, if you put on a calcium application, let's say with what I was speaking about just a moment ago, if you put on a foliar application of Holocal and Accelerate and Boron at pre-bloom and post-bloom, and again, 10 days later, let's say for the sake of discussion, you get on 3 applications before and during the cell division period, you can have a substantial impact on fruit size and quality. As we saw with the Simonian example, that was the only thing we had to work with. We did all of those fruit quality responses and size responses happened with spring foliar applications. However, I would suggest that those spring applications, it varies from operation to operation depending on how severe the problem is. But in general, I would say you would only get at best 70%, and the low side maybe 50% of the response that you would get if you did a fall application. So a fall post-harvest application is actually going to, in our experience, produce a much bigger impact than when you have just the spring application. So just to build on that, when I talk about a fall application, we don't really approach it as an either-or scenario to say you just do the fall and don't do the spring. We typically do both, where we do both the fall application and the spring application, and that's when you get the greatest impact and the greatest benefit. So I hope I answered that question well. If you have any follow-ups on that, please ask them below. Then we have another question here. Does the form of nitrogen affect the production of soft cells in the fruit during that period, during the fruit fill period, i.e. nitrate versus ammonium versus urea? Yes, it does. The form of nitrogen that has the greatest negative impact would be nitrate. So you definitely want to avoid nitrate applications during the fruit fill period. Ammonium has the least negative response. Actually, I don't know that for sure. Ammonium and urea nitrogen both have less of a response than nitrate does. But the key to remember as well is it's what we really want to have happening with nitrogen inside the fruit and inside the tree in general is we want the nitrogen that is absorbed every 24 hours to quickly be converted to proteins. And we can manage that process very well by managing magnesium and sulfur and molybdenum. I didn't point it out on the SAP analysis, but our goal is to have nitrate and ammonium levels in the SAP analysis be at 0. And ammonium levels may climb above the 0 number when we have very high temperature conditions and a very warm climate. But with nitrate, it should be possible to keep the nitrate levels at 0. In other words, let me say this a little differently. It is possible for us to have a tree that has a generous supply of total nitrogen, but the nitrate number is at 0. And that's because all that nitrate has been converted to complete proteins. So we can actually have a plant that has a generous supply of nitrogen, but doesn't have nitrates that produce soft fruit. So that's a very important piece. Great question. So Jim Porterfield asked the question, how do you measure photosynthesis so you know it is 60 to 80% of its potential? Well, you can measure it in a laboratory and actually measure what is happening in a very detailed way, but out in the field from a real practical and perhaps a simplistic perspective, we can look at this also just simply by looking at Brix readings in a refractometer, where we can monitor that we have Brix levels that are one day maybe 2 to 3 on a Brix reading, and then with a well-designed Foliar application, that number can spike to an 8 to a 10. And this is actually something that I've been talking about for a number of years that Don Huber recently confirmed for me, and he agreed that almost all of the crops that we work with today that we've come to accept as normal is plants that are photosynthesizing at about 20 to 30% of their inherent capacity. And there was some really interesting research work that was done on this, particularly on corn by Charles Tsai, TSAI, and you can look up that information online. It's fairly readily available. All right, Michael asked the question, have we done any work with nickel? Yes, we've done some experimentation with nickel. I believe that nickel is needed particularly to help convert ammonium in high temperature conditions. So when you have really warm temperatures and plants are switching from photosynthesis to respiration, then in that respiration process, you're going to get some protein degradation because plants are actually utilizing protein as an energy source and producing ammonium. So to convert that ammonium back into amino acids and into the protein, into proteins, I believe that nickel is a part of that process as an enzyme cofactor and is needed in very small amounts. However, we have found nickel applications by themselves to be inconsistent, and that nickel doesn't seem to have the effect of converting ammonium to proteins unless the plant has an adequate supply of carbohydrates and sugars from the photosynthesis process. So if you put on an application of nickel but you don't have enough sugars, you're not going to get ammonium conversion to complete proteins. So great question. Zia asked the question, what products are organically approved and what is an alternative to urea for organic use? So To the first part of your question, all of the products that I referenced earlier, the Holocal, the Accelerate, the Rebound Boron, and so forth, everything that I suggested is organically certifiable with the exception of urea. So in organic systems, we obviously need to use nitrogen in the amino acid form. So if we can get amino acid form nitrogen from, let's say, liquid fish, liquid crab, and shrimp shell products would have some, and there are some water-soluble powder amino acid nitrogen forms available as well that are from soybean extracts and so forth. So we find actually that we don't get as big an effect from the amino acid nitrogens as we do from the urea, because there is something unique about the urea biochemistry that actually contributes a lot of freeze resistance and reduced freezing temperatures to the buds. But the amino acids are still very effective and very important, even in an organic system. Another question is, how many foliar applications would you make during the cell division stage? And I had also mentioned I'd like to try to prolong that period, but I didn't mention how. So So how many foliar applications would I make during the cell division stage? I would suggest our target, what we try to achieve, is to apply 3 foliar applications before the cell division stage ends. So one of those might be a pre-bloom application, and then a second immediately post-bloom, and then a third maybe 7 days after bloom. So we try to put on those 3 applications. We have growers that try to do more and try to do the third application 5 days post-bloom or 5 days after the second application. But many of the larger growers that we're working with don't have the labor and equipment resources to cover their entire operation that quickly. So most generally, in actual practice, most of the growers that we work with are putting on either 2 or 3 applications before and during the cell division period. It would be nice if we could apply more, but in some cases we just don't have the resources to accomplish that. So I also mentioned that I'd like to try to prolong the cell division period, and how do we do that? This is a fascinating question that I'm really intrigued by. One of the main determining factors for how long the cell division period extends is actually ambient temperatures and the climate around the tree. So, of course, if you have an optimal growing environment, ideal temperatures, and ideal moisture, then that cell division period is going to expand. In some cases, it can go as long as 16 to 18 days. And this is a case where every day, in fact, every hour, can make a really substantial difference. So being able to extend that by a couple of days has the potential to be really exciting and really powerful. This is something that I'm interested in, and we are actually working on researching and understanding much better. There is some initial research that indicates using cytokinins and using seaweeds during this product. This is one of the things that we designed the Accelerate for, can perhaps expand this cell division period. But I'd say at this point, and from my own understanding at this point, is that the research is still in early days, and we have more questions than we have answers for right now. But this is something that I'm personally really excited about, because if we can expand that and extend that window, we can really have a substantial impact on fruit size. So I'm really excited about that. Great question. Jason Lindman asked the question, do you believe that calcium can be robbed from existing fruit if the demand is higher than the supply? That's an interesting question, and I would say, based on my understanding of calcium mobility and calcium flow inside the plant, I would not expect that to be the case. Calcium is generally not considered to be phloem mobile. it can be flow mobile when it is in the chelated form. So what that means is when you have calcium in the chelated form, let's say you have an amino acid chelate or a fulvic acid chelate or an EDTA chelate, you can put on a foliar application on the leaf surface, and as long as it remains in the chelated form, it can be transported from the leaf into the fruit. And this is the foundational idea behind HoloCal, where we have a fulvic acid chelated calcium that can actually move into the fruit effectively. So is it possible that a chelated calcium, but then generally what happens inside the fruit is that calcium now becomes disassociated from the chelation agent and actually is incorporated into the cells and into the cell membrane. So once it's become disassociated, it actually attaches to the cells and becomes a part of, a component of the cell membranes. And in my understanding, I'm not aware of anything that would support the idea that calcium could move out of the fruit back into the tree. With that being said, I've seen lots of interesting things that are not supposed to happen, but still sometimes things don't seem to be adding up. So I'm not aware that that could happen, and I don't think that's possible based on our currently existing knowledge. Greg Statch asked the question, is it effective to apply these minerals via drip irrigation in the fall and the spring rather than apply as a foliar spray? You can still produce a response. Particularly, I would say the greatest response that you will get if you work primarily with irrigation is in the prior season. So if you put on nutrients primarily through drip irrigation, expect to see the greatest response the following year, not the current year where you're actually doing the applications. So I would say from an economics perspective, where can you apply the least amount of product? And of course, I'm also taking labor costs and equipment costs into consideration. Where can you spend the least amount of money to have the greatest economic impact? The answer is going to be with the foliar applications. You still can get benefit, and the drip irrigation applications are still valuable. But I would say in general, they'll produce about 30 to 40% of the response that a foliar application will. A foliar application will be much faster and be much more effective and produce a much greater response. Whitmar McConnell asked the question, what are some sources that discuss manganese regulation of potassium? So I'm not aware of any published literature at this point that describes this effect that we have observed in the field. We are actually looking at conducting some very in-depth research in this next growing season, partnering with a university to try to understand what is happening and what is going on inside the plant. We have observed this purely from a very experiential perspective. So when we look at the SAP analysis, you were able to see the quality and the integrity of some of the data that we've been seeing. We now have a database of tens of thousands of SAP analysis numbers, and there is without any question a strong correlation between manganese levels and potassium and calcium ratios in the fruit. So we published an article in the American Fruit Grower a number of months ago. I think it might have been in June or July of this last year, where we described some of the effects that we were seeing. So there isn't any official peer review publication describing that at this point. That's something that I think we need to research and try to understand better. Luke Anderson asked a question, in terms of developing fruit firmness for sweet cherries, do we still recommend gibberellic acid in conjunction with this nutritional approach? So at this point, we have not discontinued gibberellic acid applications with the cherry growers that we're working with. So we are still using GA applications combined with the nutritional approach. With that being said, we have had, on an experimental basis, we have had some blocks where we did not apply gibberellic acid, and we were still developing fruit firmness well over 400 on the FermTech. So I believe it is possible to not use gibberellic acid. but it's for the effects of gibberellic acid. We haven't, on a large scale at this point, we haven't discontinued the use of GA. We're still using it. Michael Borke asked the question, in potatoes, calcium can be increased by using plant vegetable fats. Is this also true in stone fruit? Michael, this is a really intriguing question. I don't know the answer to that. I wasn't aware that calcium could be increased by using plant vegetable fats in potatoes, and I'm really interested in learning more about that because I'm really fascinated with the biochemistry of what happens with fats inside plants. And if we can find that there's some association between increasing fat concentrations in the fruit and increasing calcium levels in the fruit, that has the potential to be really important and really valuable information, because that would now mean that we can possibly use fatty acids to move calcium into the fruit much more effectively. And I can see where it could be possible, because you have an association with lipids and calcium in the cell membranes. So that's a really interesting question. I'm not familiar or not aware of any research in potatoes or any other crops. So if you can send us some of that information, I would be really intrigued to learn more about that. It's a great question. Greg asked the question, I've been applying calcium on the ground in the fall for grapes. I almost always see leaf signs of severe lack of potassium on basal leaves within 4 weeks after bloom, even though I apply potassium via foliar about this time. Am I waiting too long to start potassium foliar sprays? Can I apply some or all of this potassium via drip irrigation? These are great questions, Greg. So based on what you described, I would say that yes, you can begin applying the potassium earlier. You can begin applying it so immediately after the cell division stage. So that would generally be, I would say, if you go 20 days after blossoming and pollination, you're going to be outside the cell division window. So you could perhaps move up your first potassium applications by about 10 days. And then to your next question, can you apply some of this potassium via drip irrigation? I would say the answer is yes, because plants, potassium is one of the most rapidly absorbed nutrients from the soil profile. The only other elements that come close are chloride and sodium, and to some degree nitrate. So potassium can be absorbed very easily, very quickly through the soil profile, and it would seem to me that you could apply potassium in the drip irrigation, at least some of it, and perhaps even all of it, starting 20 days after pollination, have the plants absorb it very quickly. So I definitely think that you can do that. Luke Anderson asked the question, what has the greatest effect on return bloom for sweet cherries? Is there a strategy to maintain yields year after year? Yes, there is a strategy, and it's the same strategy for sweet cherries or apples or any of the stone fruit or any of the tree fruit for that matter. So the key question to ask is, when are the reproductive buds for the following year's crop being determined? So on sweet cherries, if I recall correctly, the buds for the following year's crop are being determined on the bud initiation stage is happening in June, while this year's crop is still on the tree. I'm now not completely certain of that. There's some slight variation among some of the stone fruit, but so I may be corrected on that, but it's in that general time frame. The key is you want at that moment during the bud initiation period, the plant from a hormonal perspective is switching from vegetative to slightly reproductive, where you have a slight degree of reproductive dominance. So you want to use nutrient applications that support and enhance that switch to reproductive dominance. So At that specific stage, which is typically also going to be about a 2-week time window, anywhere from 14 to 21 day time window, you want to apply cytokinins, high levels of manganese, boron. So this is, again, what we designed Accelerate to do. So a foliar application or 2 foliar applications of Accelerate right at the bud initiation period is going to help produce the greatest number of buds for the following year's crop. And this is essentially, we use this strategy on apples and pears and other crops to reduce or eliminate biennial bearing. So you need to target that specific window of when the bud initiation is actually happening, and you can substantially shift the number of buds for the following year's crop. Great question, Luke. One anonymous contributor commented on my comments about an organic alternative for urea. I believe an organic alternative for urea is Sobek or Vesta, certified organic. So I'm assuming those are product brand names, certified organic by the state of Oregon. I've used it in California. And if you want the additional information on these products, if you want help sourcing organic forms of nitrogen, speak with Jeff McInnes or talk to the team at AEA. I'm sure they can help you put something together and figure that out. All right, we'll take one more question here. And my goodness, you guys are asking so many questions, and I see there's a bunch of questions in the chat as well. Let me review these really quickly. John asked a really great question, from John Meredith. How do you cost effectively move calcium into the tree during the cell division stage when there is just the spur leaf on the peach tree? There is very little leaves on the tree for foliar during that time. This is an awesome question. It's a great question, John. And the answer is fascinating and intriguing. So first of all, the spur leaf is the most important. So obviously we want to get calcium in the spur leaf to move it into the fruit because that's where we have the greatest impact. But I've been surprised and amazed at some of the research that I've seen where they have been studying the absorption of nutrients by the bark. And so we tend to think of nutrient absorption primarily happening through the leaves, but in fact, the evidence suggests that bark can perhaps absorb nutrients even more effectively and faster than the leaf tissue. So we're actually getting nutrient absorption through the bark and into the twigs and branches and moving from there into the buds as well. So I've always wondered how some of the early foliar applications, and sometimes we're putting on foliar applications when there is barely any vegetation present at all, and yet we're seeing a tree response and a crop response from that. And I believe that is how that is happening. So that's a great question. There's one final question here. John Warmerdam asked the question in a previous webinar. We spoke about soil bacteria. Can I speak about the importance of soil biology in permanent crops such as trees? Yes. This is really a topic for an entire conversation in and of itself. Very simply, if I'm really intrigued about the question earlier about potential fat content being associated with calcium movement into the fruit. There's this entire this entire ball of wax that is associated in my mind when I think of soil biology. What soil biology means to me in terms of plant responses, it means that all of a sudden the plants are now absorbing the majority of their nutrients in the form of microbial metabolites. So you now have amino acid chelates and organic acid chelates of calcium and magnesium and zinc and manganese and all these various minerals from the soil profile. And that means that these minerals are absorbed by the plants much more effectively and much more efficiently. and translocated much more rapidly. So now when you have, let's say you have a citric acid chelated calcium from the soil profile, that's going to move into the fruit much more rapidly and much more quickly than just ionic calcium. So when you have aggressive bacterial populations in the rhizosphere, that's one thing that will happen, is that you get much better nutrient absorption of all nutrients, particularly all the difficult to absorb nutrients like calcium and phosphorus and so forth. But the second piece that happens is when you have these really aggressive bacterial communities, because of much better nutrient absorption, you now also have increased lipid concentrations and fat concentrations. So you see this glossy, waxy sheen on the leaf surface, and that is really an expression of high lipid content and high fat content in the leaf, which is also going to be an expression of strong cell membrane integrity in the fruit itself. So if we want to produce really firm fruit, then one of the keys with calcium is we want every cell to have a very strong cell membrane. And not only does calcium contribute to that, but lipids contribute to that as well. So what I would just summarize very simply is to say that soil biology and strong and aggressive bacterial communities in the rhizosphere are foundational. They're fundamental to producing disease resistance and to producing these high quality fruit and firm large fruit that we're talking about. Everything really rests on the foundation of really good biology. So I want to thank all of you for attending tonight. I hope you enjoyed this webinar. And if you have any follow-up questions, feel free to email or call directly to speak to some of the members of the AEA team, our consulting team. We have a really great team and they really enjoy hearing from all of you. So thanks for attending tonight. Have a wonderful evening, and I hope to talk with all of you soon. Be well. Bye.